Why does hot air rise? So here's a picture of a beautiful hot air balloon. I was always sort of mystified by these things as a child. Like, how does that work? We understand a helium balloon, you fill it up with helium and you tie it off. But here's this giant balloon, and it's open at the bottom, and there's actually a little tiny opening at the top too, oftentimes. And it's huge, and you've got this burner in here, and it goes up, and it'll even lift people. Like, what on earth is going on there? Well, it's hot air. When you heat a gas, it gets larger. It expands its volume. I don't know if this has happened to you. My kids would go to parties and they'd get balloons, right? And if it's in the winter and you come home, it's late, they're asleep, you forget the balloons in the car. You go out the next morning and it's cold, right? Winter. And the balloons are kind of small and they're sitting on the floor. You bring them inside where they warm up and they get a little bigger and they start to float again. What's going on with that? Well, it's a temperature difference. The volume of a gas is dependent on its temperature. When you heat up a gas, the mass doesn't change, but the volume does, so the density changes. So when you heat the air in here, it expands and its density goes down, and a less dense gas floats in a gas that's more dense. That's why helium floats. It's because it has a lower density than air. Your question?
Air quality in the winter is worse because of this,
Air quality in the winter, there are a lot of factors that affect air quality. But we do get the inversion layer, right? And that causes, that traps air down with us and doesn't allow the pollutants to disperse. So things like this do have impact on stuff like that. So this is Charles' law relating volume and temperature. And so what we find is if we take a gas and we heat it, so here's 0 Celsius, and we heat it. As you heat it up, the volume, where's my pointer? The volume increases in a linear fashion. So you can graph these points, and here's 0 Celsius. But these form a straight line, and if you draw that straight line through at 0 volume, that would occur at minus 273 degrees Celsius. Was that cold? Yeah, this is really, really cold. 0 degrees Celsius is the freezing point of water. 100 degrees Celsius is boiling, right? So 100 is a lot warmer. So this is more than twice lower than the freezing point of water, really cold. But they observed that this would have a y-intercept of 0 at minus 273. When you have the equation of a line is y equals mx plus b. That's the form where b is the y-intercept, where it crosses. And so if b is 0, the line gets much simpler to deal with, because then you just have y equals mx. And so observations like this are what led to a new temperature scale, the Kelvin scale. They said, well, wouldn't it be convenient if this was 0 on the temperature scale, and then the intercept here would be 0, 0. This is predicting also the lowest possible temperature. Think about taking a sample of a gas and cooling it down and get smaller and smaller and smaller and smaller. Could it ever have a negative volume? No, negative volume is not possible. So this is called 273. No, it's not called. Where did that come from? There's just things coming out of my head. It's called absolute zero. I can't even read today. Minus 273 degrees Celsius is called absolute zero. And there are scientists actively trying to achieve absolute zero, and nobody's quite gotten there. They've gotten really, really close. Less than 1 degree off, but nobody's gotten there yet. So Charles, he was in 1700s to 1800s. He was actually not a chemist, but he was a French mathematician and physicist. And he looked at this relationship between volume and temperature of a gas. Now this is assuming that pressure stays the same, because we saw that pressure and volume, if you change the pressure, you're going to change the volume of a gas. So we're going to keep the pressure constant and the amount of gas constant. And so one way to state Charles' law is that the volume is proportional to the temperature. But the temperature has to be on the Kelvin scale. Because this is saying volume is equal to some constant times temperature. That would have, for that line, it would have an intercept of 0. If we're doing Celsius, this is not going to be 0, and it's not going to work out very well. So very important that it be the Kelvin temperature. When the temperature doubles in kelvins, the volume doubles. Okay, so this is really, really important here. All caps. I'm going to draw a box around it. There's an exclamation point at the end. I'm going to put asterisks. For gas laws, the temperatures have to be in kelvins. Have to. Doesn't work otherwise. They will give you the temperatures in Celsius, and they'll sometimes ask you to report your answer in Celsius. I've never actually seen a thermometer that's labeled in kelvins. The conversion is so simple. Nobody needs that. Remember that now I'm blanking. Yes, okay. The Kelvin temperature is equal to the Celsius temperature plus 273. So you fix it into kelvins first, and then this is true. And this is the reason the equation of the line is y equals mx plus b, and by using the Kelvin scale, that y-intercept is 0. So this goes away, and now we have the volume being proportional to the temperature. Kinetic molecular theory explains this law as well. That's what theories do. They explain our observations. The law says what happens, the theory says why. So if we increase the temperature of a gas, what does that do to how fast the particles are moving? It increases. Barefoot people on the sand, right? Hot sand, people move fast. So you increase the temperature, the gas particles move faster. Are they going to run into the walls more often? Yeah, they will. If the pressure's going to stay the same, then it has to get larger. So the volume increases. This is something you can try at home. You know, we always get all these warnings, don't try this at home, right? So I think it's fun to say, yeah, go ahead and try this at home. Blow up a balloon and stick it in some ice water and watch it shrink. That's what Charles' law says. The volume goes down when the temperature goes down. And then take the balloon and put it in some boiling water or even just some really hot water and watch it get big again. You can go back and forth until the balloon pops or you get bored, right? Make it big, make it small. The temperature and the volume are proportional. So we can express Charles' law this way. The volume 1 over T1 equals volume 2 over T2. All temperatures must be expressed in kelvins. You got that? What temperature scale do we use for gases? kelvins, you're still going to forget. So let's do an example. A sample of a gas has a volume of 2.80 liters at an unknown temperature. When the sample is submerged in ice water at 0 degrees Celsius, its volume decreases to 2.57 liters. What was its initial temperature? In kelvins and in Celsius. We read through the problem, and we see that we're talking about volumes and temperatures. So that's going to be Charles' law. So Charles' law, V1 over T1 equals V2 over T2. So we're going to make a table to organize the information that we have. We've got condition 1 and 2. If you're doing a problem and your friend is doing a problem and you've got your 1s and 2s backwards, that's not a problem. As long as you have the correct temperature and volume associated with each other, it doesn't matter if you call it 1 or 2, it's still going to work out just fine. So the first number I come to is 2.80 liters. So I'm going to write that down, 2.80 liters. That's a volume. I'm going to label that column volume. At an unknown temperature. Okay, well, it's unknown. I can't write anything down. When the sample is submerged in ice water, something has changed now. We took the sample, we put it in ice water at 0 degrees Celsius. That's a temperature. And this is the second condition, 0 Celsius. What temperature scale do we need to use? Kelvin. Let's convert it right now, because if we wait, we'll probably forget. Plus 273, so that is 273 Kelvin. And I'll just make my table a little bigger. It's fine. This is temperature. So at 0 Celsius, volume decreases to 2.57 liters. 2.57 liters goes in here. What's the initial temperature? Well, we have a blank in our table. The way these should work out is you make a table like this and you should have one empty square or a rectangle, as the case may be. So I'm going to call that T1. Now we're going to look at the equation we're going to use here, and we need to solve for T1. This equation has fractions in it. My friend who teaches middle school math says that fractions are the F word. That's what most middle school students feel. When we have fractions in here, we need to be really careful. My experience is students make a lot of mistakes. So let's get rid of the fractions first. The way we get rid of fractions in an equation like this is called cross-multiplying. So to cross-multiply, I'm going to take the top of one side and multiply by the bottom of the other. And then the bottom of this side times the top of that side. You see this cross? We're multiplying, and it's crossing, cross-multiplying. So when I do that, I get V1 T2 equals T1 V2. Everybody still with me? See how I did that? So we're going to get rid of the fractions, and now this equation is easier to rearrange. I'm trying to isolate T1. I need to get rid of V2. So I'm going to divide by V2, so those cancel out. If I do it to one side, I have to do it to the other side. It's like dealing with two children. If you give one a cookie, you have to give the other a cookie. If you give one a sports car for his 16th birthday, you have to give the other one, or you'll never hear the end of it, right? Same thing to both sides. So now I've got T1 equals V1 T2 over V2. Just copy carefully. Now I go to my table and I find those numbers and I stick them in with their units. V1 was 2.80 liters. Don't have a lot of space, that's okay. 273 Kelvin. And V2 was 2.57 liters. The liters cancel out. So temperature 1 is 2.8 times 273 divided by 2.57. And how many significant figures should my answer have? 3. Most problems that this author writes in the textbook, most of the problems have about 3 significant figures. So, if that was some sig figs or something that just really mystifies you, round everything to 3 sig figs and you'll probably be good enough. What's the unit on that? Kelvin. Question also asks for the temperature in Celsius. So I'm going to take 297 and subtract 273. That equals 24 degrees Celsius. Is that a reasonable answer? Yeah, 24 degrees Celsius is a room temperature. So you took a balloon at room temperature, you put it in ice water at 0, the volume went down. What would happen in this problem if we didn't use Kelvin? What if we had 0 degrees Celsius in here? You see that? Yeah. What would my T1 end up being? 0? Does that make any sense? No. It doesn't work if the temperature's in Celsius. Sometimes you'll end up dividing by 0. Your calculator doesn't like that. You can't divide by 0. Any questions?